welcome back to topic 31 for Algebra 1, Exponential Growth and Decay Functions. In part 4, we're going to compare linear and exponential functions and identify, is the example linear, exponential, or neither? And if it's linear exponential, we're going to write the equation. Looking at the first example, we have our values for x and y, and specifically we want to look at our y values to identify if there is a common multiplier or if there's a common difference. So looking at our y values, we go from 20 to 10, 10 to 5, 5 to 2.5. So what is happening here? Well, in order to get from 20 to 10, we can either subtract 10 or we can multiply by 1/2. Let's try the next one. In order to get from 10 to 5, we can either subtract 5 or multiply by 1/2. So what's happening here is we are multiplying each value by 1/2. So because we have this consistent multiplier here, this is an exponential function. And we have a common multiplier of 1/2. Now, if we want to write a formula, we have y equals a times b to the x. A is my y-intercept. Well, I can identify my y-intercept by looking at my graph. It's when x equals 0. So my equation will be y equals 10 times my multiplier, which is 1/2 to the x power. Looking at the next example, we go from 1 to 4, 4 to 9, 9 to 16. Well, to get from 1 to 4, we can multiply by 4, or we can add 3. To get from 4 to 9, we have to multiply by a fraction or add 5. So here, we're not getting consistent. We don't have anything that's consistent. And especially if we go from 9 to 16, here we have to add 7, and we would also multiply by a fraction. So for this value, it's neither exponential nor linear. For the next problem, let's go with a different color here. For the next problem, we go from 16 to 12, 12 to 8, 8 to 4. Well, from 16 to 12, we can subtract 4. From 12 to 8, we can also subtract 4. And from 8 to 4, we also subtract 4. So this is an example of a linear model with a common difference of -4. And if we want to look at the x value, in this case, we add 1 every time. And that's going to come in handy with our next step. So for a linear equation, we can model that with y equals mx plus b, where m is my slope and b is my y-intercept. So we note here, by when x equals 0, my y-intercept is 12, so I can plug that in. My slope, on the other hand, I can look at my common difference. Now this is really -4, because I'm changing by -4 if I want to use the table method. But I also have to make sure I look at the change in x as well, because slope is change in y over change in x. So here, I would have -4 over +1. If I simplify that, I get y equals -4x plus 12. Looking at the last example, we go from 8 to 12, 12 to 18, 18 to 27. So what's happening here? Well, we could be adding And it seems kind of consistent except for this 27 down here. So let's see if we can multiply by anything. In order to get from 8 to 12, we can multiply by 1.5, or 3/2. In order to get from 12 to 18, we're also multiplying by 1.5. And to get from 18 to 27, we also multiply by 1.5. So here we know that this is exponential because we have a common multiplier of 1.5, or 3/2. If we want to write our exponential model, y equals ab to the x, we would get y equals, now our y-intercept is when x equals 0, so we have 12 here, and our multiplier is 1.5, or 3/2, to the x power. And that is